Hello everyone, my name is Sheikh Ahmed Pasha and my caption project 3 is Cardiovascular Risk Prediction. And the problem statement of our project is the data set provided for the project is an ongoing cardiovascular study on residents of the town of Framingham and Massachusetts. And the classification goal is to predict whether the patient has a 10-year risk of coronary heart disease. And the data set has patient's information, so like the behavioral and the medical condition of the particular patient, and it includes over 4,000 records. That means 4,000 patients, and with the 15 attributes, and each attribute is a potential risk factor, and there are both demographic, behavioral, and medical risk factor. So our main objective behind the project is a classification. Is a classification whether the person has a risk or not. And the workflow, if you see the workflow of our project, there are 7 stages. And the first stage is data understanding. Here we will understand the data. And the second stage is data cleaning and data manipulation. Here we will clean the data and manipulate the data as of our need. And the third stage is exploratory data analysis. Here we deep dive into the data and explore some key factors. And the fourth stage is feature engineering. And fifth stage is a pre-processing of the data, and the sixth stage is model implementation. Here we implement the data into the models, and yeah, the seventh stage is model explainability, like feature importances of the models. And the first stage is nothing but first stage is data understanding. Here we understand the data after importing the several libraries like pandas, numpy, and matplotlib for visualizations. We first we read the data. We read the data, and after reading the data we can see that there are 3,390 rows with the 17 columns. And it contains a patient's health information like demographic, behavior, and medical risk factors. If you see, the features has mainly 4 types. One is demographic. Demographic means it's a sex and age. Sex means is a male or a female, and age is a age of the patient. And behavior means, we see, is smoking is a feature. It contains yes or no. And if the person have a habit of smoking, it shows yes. And the person doesn't have a habit of smoking, it shows no. And 6 per day, like how many cigarettes the particular patient smokes per day. And medical is history and the current. Means history means any historical medical information, and a medical current means it includes the current medical conditions. And if you see medical history, BP meds, that means whether the patient is on blood pressure, is on BP medication or not. And the prevalent stroke, whether the patient has previously had a stroke or not. And the prevalent height means whether or not the patient was hypertensive. And diabetes, whether or not the patient has a diabetes. And medical current means the current medical condition of the patient. And if you see, the total call means nothing but a total cholesterol level, and cis-BP means systolic blood pressure, and diabetes means diastolic blood pressure. And BMI is a body mass index, heart rate is a heart rate, and glucose is a glucose level. And here the predicted feature, the predicted variable is a 10-year risk of coronary heart disease. And it contains only two values, and 1 and 0. 1 means the patient has a risk of the disease, and 0 means the patient doesn't have a risk of disease. And the stage two is data cleaning and data manipulation. Here we will check for the null values and the duplicated values. As our data has zero duplicated values, but our data has null values. And there are 7 features with null values. And those are education and 6 per day and BP meds and total call and BP, BMI and heart rate and glucose. So before handling these null value, these features which has null values, we have to observe the distribution of these features, or the distribution of these features with null values. So these are the distribution of the features with null values. So if you see education is this is type of a discrete feature. Like this is not a continuous. There are only four values, 1, 2, and 3, 4. and after that 6 per day. It is a continuous feature because there are more values. And if you see BP meds, there are only two possible values. One is 0 and one is 1. And 0 is in high. And the total call is also a continuous feature. And BMI is also a continuous feature. Heart rate is also a continuous feature. And glucose is also a continuous feature. So here we can observe that education and BP meds are a discrete features. And other than those, all are continuous features. So So all the above here we can observe that all the continuous features are skewed towards the right. That means they are positively skewed. So we can replace the null values of those features with a median value. And if you see education and BP meds, which are discrete features, we can replace the null values of those features with the most frequent value. That is nothing but mode. So here we can handle the null value. Here we handle the null values, and the third stage is exploratory data analysis. And the first step in exploratory data analysis is to understanding about the features and what are the features, like types of features, like what are the numerical features, what are the categorical features, and in numerical features, what are the discrete features, what are the continuous features. So we can see that here the continuous features and discrete features and categorical features. So after dividing the features into numerical and the categorical, we can observe the distributions. So first, we can observe the distributions of numerical features. Here we can see the distribution of numerical features, like uh, here some features are to be categorical, should be categorical. Like if you see education, there are only four values, and also BP meds, there are only two values, and prevalent stroke, there are only two values, and prevalent health, there are only two values, and diabetes, there are only two values. These are the discrete variables. Other than that, most of the are continuous features. And from these distribution plots, so we can observe that most number of patients age falls in the range of 35 to 45, and the most number of patients belongs to education category 1, and most number of the patients smokes cigarette in the range of 0 to 1. And if you see cigarettes per day, and very few patients drinks more than 40 cigarettes. And most number of patients are not on BP medication, and most number of the patients also doesn't have a stroke previously, and most number of patients are not hypertensive and not bad diabetic also. Most number of patients cholesterol falls in the range of 200 to 300. Here we can see the uh, most number of the values falls in the range of these values. And after that we can observe the distribution of categorical features. Here we have only two categorical features, and those are sex and is smoking. So sex means it's nothing but a female or a male. Here we can see most of the patients are females. And if you see is smoking, almost half of the patients have a habit of smoking. And here we can observe the relationship between the continuous features and the target feature. Target feature is a 10-year CHP, and here you can see that age, except in the age, all the other continuous features has some relevant number of outliers. So if you see the age is towards the, if you see the box plot of age, the age is the age for the one category, the age is more. And here we can also see the total cholesterol for the one category. The total cholesterol is more, and also for the systolic BP, and also for the diastolic BP also, and also for the PMI. And here we can see that, and also for the heart rate also, there is a little bit more, and for also the glucose also. That means the features, if these features like age and total cholesterol and systolic BP, diastolic BP, and BMI, and heart rate and the glucose, and these features values increases, the risk also increases. The risk also increases. That is a conclusion we can derive from these box plots, and that is, and here the featured cigarettes per day is equally distributed. Equally distributed. That means this feature is may not be a good predictor. And here we can observe that how discrete features are distributed among the target feature. Like if you see in the for example, in the education feature, there are four categories like one, two, three, four. Okay, in one category, how many people have risk and how many people doesn't have a risk. Likewise, in a BP meds, there are two categories. One is one is the patient who doesn't on a BP medication, and the patient who has on BP medication. There are two categories. In those two categories, how many have a risk? How many have doesn't have a risk? Likewise, in diabetes also, diabetes are two categories. One is the patient has a risk, the patient has a diabetes, and the patient doesn't have a diabetes. So, if you see among these two categories, what are the count of the people who have a risk and who doesn't have a risk? Likewise, in prevalent prevalent stroke, here we can observe that the how many people in those categories have a risk and no have and also doesn't have a risk. Likewise, how categorical features also distributed among the target feature. And after that, a correlation heat map. And correlation heat map, from this correlation heat map, we can observe that there are some features which are correlated with each other. Like means, if you observe, there is a dark green or a light green. There is a dark green or light green value boxes in the correlation heat map. That means those features are correlated. If you see, smoking and cigarettes per day are 76% correlated with each other, and the prevalent hype and systolic blood pressure are 70% correlated with each other, and systolic blood pressure and diastolic blood pressure are 78% correlated with each other. And prevalent hyper and diastolic blood pressure are 61% correlated with each other, and glucose and diabetes are 61% correlated with each other. So we have to remove multicollinearity. So we'll see this in a we will handle multicollinearity in the feature engineering, and the next stage is a feature engineering. Okay, in the feature engineering, the first step is to convert the data into numerical form. Like we have two categorical features, so we have to convert those two categorical features into numerical features. Like for example, we have sex and e-smoking. These two features with categorical features. So we'll convert these two features into numerical features, and after that we will remove the multicollinearity. So we have to, in removing multicollinearity, we know that cis-BP and IBP are 71% correlated with each other. So uh, we created a new column. So because you can observe that those two are blood pressures only. So systolic blood pressure means the pressure in your arteries when your heart beats, and diastolic blood pressure means the pressure in your arteries when your heart rests between the beats. So diastolic blood pressure minus systolic blood pressure is pulse pressure. So we can create a new column, pulse pressure, from these two columns. So after that, we can remove the systolic blood pressure and diastolic blood pressure because we created a new column from those, and we can also remove prevalent hype and easy smoking because easy smoking is highly correlated with the cigarettes per day. And after removing these features, our data has no multicollinearity. And after that, we can handle outliers because outliers are the because removing outliers is very important. And at first, I created a for loop for all the numerical features, which happens the outlier index. So we can identify the outliers index by this for loop, which is based on Z score. And after identifying those outliers, we can easily remove them from the data. And after the data pre-processing means after converting the category which is into numerical features, our data has only numerical features. And feature scaling is a very important step. Here we use the standard scaler. to scale the features. And after scaling the data, the data is ready to fit into the model. And after that, we can split the data into two sets. Like one is a training data set and another is a test data set, which we will evaluate the model by using a test data set. And here the test data set with the size of 20%. I splitted the data. And another one is handling class imbalance of a target feature. Here we can observe that, so here 10 years CHD is our dependent variable. Like that is our target feature. And we can see it contains two values, 0 and 1. 0 means the person has no risk, and 1 means the person has a risk. So if you observe, 2,859 patients have no risk, and only 489 have a risk. So here uh, we have to resample the data, sample the data to equal those numbers 0 and 1s. So we used smart tech to resample the training data set into equal classes. So after that, a model implementation. So I created a model pipeline which consists of uh, classification algorithms, and then iterate through them, the train and the test and the predict and evaluate. And those classification algorithms are logistic regression and decision tree, random forest and support vector mission, and k nearest neighbors and naive bayes. And for the classification task, there are various metrics used for the evaluation, because metrics we have to choose the correct metrics for our problem statement. Because for our problem statement, we have two cases. And case one is if a person has a disease, has a risk, but the model shows no risk. So here, if you want to focus on this, we have to use a recall. So recall is a best metric for this case. And another case two is if a person has no risk of disease, but the model predicts the person has a risk of disease. So for this, if you want to focus more on this, you want to reduce more on this, the precision is the best evaluation metric. So if both cases, that means if a person has a disease but model shows the person has no risk, and also if a person has no risk of disease but the model predicts the person has a risk, if you focus on both these two, then we have to consider f1 score. So f1 score for this case, we have to, if we have to focus on both these cases, we have to use a f1 evaluation method. And after that, confusion matrix. So after fitting the data into these six classification models, first we have to evaluate the training data. Like if you see the confusion matrix, it simply shows 0 and 1 actual values, predicted values. So first, logistic regression. So after training the model, after training the model, these visualizations are the confusion matrix of for the training data. Like if you see in a 0, the model correctly predicts 1527 zeros and 1521 ones and 753. What is 753 means? 753 means the person has a risk, but it shows the person has not risk. And 747, what is 747 means? The person has no risk, but it shows a risk. And likewise, you can observe that for a SVM model also, and for KNN model, and for also decision tree and random forest and naive bayes. Like if you see for logistic regression, let's observe for the logistic regression, 1527 is a true negative, value, and 1521 is the true positive value, and 573 is the false positive, and for 747 is a false negative. That means a false positive is 753. So if you want to reduce this number, that means if a person has a risk but the model predicts the person doesn't have a risk, so if you want to reduce the false negative, sorry, false positive value 753, we have to reduce this number. If you want to consider the case one, if you want to focus important morely on the case one, we have to consider this 753 box. So if you see out of these models, this is the only for train data. Okay, and this is the evaluation metrics data frame of train data. If you see the recall and F1 score and precision score and accuracy of all the models like logistic regression, SVM, KNN, decision tree, random forest, and BES. From the above visualization and data frame, we can say that the decision tree and the random forest model are overfitted, and these models are overfitted. And after that, we have to evaluate the model by using the test data. Here we can see that the false positive value, the least is logistic regression. That means if a person here it's only wrongly predicted 33 values which have a disease, but it shows it has a no risk. And these are the evaluation metrics for the test data. And here we can see various models, evaluation metrics like precision, recall, F1 score. And from the above matrix data frame, we can say that if a recall is important and we want to focus on case one, and then logistic regression and equivalent models are preferable. Because if you want to focus on case two, that is precision is important, then naive-based model is preferable. And if a F score is important, that means if you want to if recall and the precision both are important, then we want to prefer a logistic regression model. And after that, just tune the hyperparameters of each model. So let's see logistic regression with hyperparameter tuning. Here, after hyperparameter tuning, the best hyperparameters are C equal to 1, maximum meter equal to 100, penalty is L2. And we can see the feature importance. The age feature has a more importance, and it has a recall of 66 and a precision of 23% and F1 score of 34%. And if you see this is the precision recall F1 support. This is the classification report of the model. Support vector mission with the hyperparameter tuning. Here, the best parameters are kernel equal to linear and C equal to 1. And this is the confusion matrix of the test data. And this is the precision recall F1 score support. This is a classification report. And for this model also, age is has a more feature importance, and it has a F1 score of 34%. And recall score of 68% and precision score of 23%. And KNN classifier with a hyperparameter tuning. Here, after hyperparameter tuning, the best parameter is n neighbors is equal to 2. And here we can see the confusion matrix for test data and classification report and evaluation matrix. It has a 26% F1 score and 29% recall and 23% precision. And decision tree class and decision tree classifier with a hyperparameter tuning. After tuning the hyperparameters of the decision tree, we get the best parameters are a criterion equal to Gini and maximum depth equal to 9 and minimal sample self equal to 1 and the minimal sample split is equal to 6. Here we can see the confusion matrix. It's wrongly predicted 72 values. That means who has a disease, but it shows doesn't has a disease, and 126 values of which has a which doesn't have a risk but it shows a risk. And here also you can see the age is the most important feature for this model. And you can see the precision is 17% and recall is 26 and F1 score is 20%. And random forest classifier with hyperparameter tuning. And after tuning the hyperparameters for this model, we can say that maximum depth 16 and an estimate is equal to 265. Here we can see that confusion matrix and classification report. And here also age is the most important feature. And precision of 24%, recall of 18%, and difference score of 20%. And the conclusion after these project after all these processes from the exploratory data analysis, we can conclude that half of the patients have a habit of smoking and outliers present in continuous features except the age column. And the patients who have more age and the total cholesterol and more systolic blood pressure and more diastolic blood pressure and more BMI, more heart rate and more glucose are tending towards a risk of coronary heart disease. And here we can observe that 58.4% of females and 41.5% of males have no risk of CHD, and 46.7% of females and 53.22% of males have a risk of CHD. Likewise, we can observe that we can among the people who smoke and who doesn't smoke, like 50.9% of people who doesn't smoke have no risk of CHD, and 49% of people who smoke have no risk of CHD, and 46.1% of people who doesn't smoke have a risk of CHD. Likewise, 53% of people who smoke have a risk of CHD. And after cleaning the data, after pre-processing the data, the model is ready to fit into the model. And after fitting the data into various classification models and evaluating with the test data, we can conclude that for our problem statement, there are two cases. And the case one is if a person has a disease, but the model predicts the person has no risk. That means if you want to focus more on this case, okay, you should consider a recall evaluation metric. And the case two is if a person has no risk of a disease, but the model predicts the person has a risk. If you want to focus more on this, then we have to pick a precision evaluation metric for this case. And if above both cases are important, then we should consider F1 score evaluation metric. So among after all the fitting that after fitting the data into the models, if a recall is important, that means if you want to focus on case when the logistic regression and the KNN models are preferable, and if a precision is important, that is if you want to focus more on case two, then naive-based model is preferable. If F score is important, that is if you want to focus more on case 1 and case 2, both are important, then logistic regression is a best model. And for random for all the classification models, age is a most age has a more importance, more feature importance. Thank you.